Hi folks, welcome back to Physics with Captain Rod. The purpose of this video is to provide an example of a relatively simple circuit problem. So what we're going to do is we're going to imagine that this 12-volt battery is used to drive current through this pair of light bulbs, which are going to be hooked in parallel. In this example, we're going to assume this is a 5 ohm resistor bulb and this one's a 2 ohm resistor bulb. So first of all, let's talk about, what would a parallel setup look like? So if these are wired in parallel, that means I'm going to have a wire coming here, and one wire essentially will be connected to the bulb in some way like this, and the other wire maybe something like this. And then the other sides of the connection come back together, and then presumably through a switch, and then back around to the battery. So that's an example of a parallel type of setup. And again, what makes them in parallel is this. If I were to color code the potentials, if you see my video on circuits, I like to do that. This would all be one potential up to this point here and here. Now the reason I know that is because this is presumably all wire made of copper. And if you think back or maybe look back through my videos about conducting materials, conductors themselves are equipotentials. So if this is a 12-volt potential, this would all be 12 volts up to here and then to here. Now we would get a voltage drop because of the filament of the bulb. This would all be one potential as well. And again, if we close the switch, this would all be a constant potential to here. So you'll notice that the potential difference of the battery is red to black. That's the 12-volt potential. And you look at the bulb, red to black, red to black. So this picture is an example of what's called a parallel combination. Again, the defining characteristic of a parallel combination is that the voltages are the same across each element. So again, red to black, that's a 12-volt potential from here to here, and over here, 12-volt potential from here to here. Now next, let's talk a little bit about the circuit diagram. This is just what I would call a sketch describing the problem. Here's what the circuit diagram might look like. I'm going to put the battery in first. So I'm going to put a voltage symbol for the battery, and again, the long terminal represents the long guy here represents the positive terminal of the battery, and the short guy the negative terminal. And then I'm going to put a resistor here and call it R1 for this bulb, where that's my value of R1. And again, in parallel, here's the second resistor, which I'm going to call R2. And then again, these have to come back around through a switch into the bottom end of the battery. I'm going to go ahead and just leave the switch off and just assume it's closed in this problem now. Now, again, I like in all these circuit diagrams, I really like talking about potential differences. So this is all conducting material up to the bulb. So this is all one potential. I'm going to go ahead and color code that red. Now, the actual value of that potential doesn't really matter. And, just like potential energies, you can actually zero a potential wherever you want. If I decided to call the potential here 0, then red is 12 volts higher. This would be plus 12. If I wanted to, though, I could call this, 6 volts. And this would be 12 volts higher. This would be 18. Or I could call this minus 6, and then this would be 12 volts higher, plus 6. Any one of those combinations is correct. The only thing that matters is the difference in between these is 12. If I called this 0, then the red would be a 12-volt potential. I'm going to go ahead and do that. Just call that potential there 12 volts. And again, I have now defined a 0 here. We're calling that 0 volts. All right, now notice that black to red is 12 volts, and I can apply that right here. Black to red, the potential across this bulb is 12 volts. So when we apply Ohm's law to this bulb, V equals IR1, the voltage is 12 volts. The I we don't know. The resistance, again, that's the 5 ohm resistor. So R1 is 5 ohms. And we can solve that for the current. I'm going to call I1. That's going to be the current through that bulb, which is 12 volts, or it's 2.4 amps. So now we know that the current anywhere in this branch is 2.4 amps. So I'm going to go ahead and in this picture maybe put my current I1. We just found that 2.4 amps. Right? Bulb 2. Now you'll notice that red is 12 volts, black is 0. So the current through R2 is going to go this way. Current always goes from higher to lower potential. We can find that current by writing down Ohm's law, V equals IR. Taking note that the voltage is, again, red to black, that's a 12 volt potential difference. The I2 we'll know in a minute, and the resistance is 2 ohms. Oops. So the current I2 in this case is going to be 6 amps. All right, last, let's go ahead and get the current that would be coming from the battery, and I'm going to put that here in the picture. IB. It's very important to recognize that, the battery, this is not like current just coming out of the battery. Whatever goes out of the battery has to go in. This current IB must be going in over on the other side. So I'm going to go ahead and put IB here. Whatever the value is of this current, it's got to be the same anywhere from here to there in that problem. All right, again, go back and look at my video on batteries if you're wondering about what I'm talking about. Batteries are not, do not really have a net current per se. What they do is they drive a current in the circuit. But if I were to surround this with a surface here, the net change in charge for that surface is 0. We have charge leaving here and we have charge coming in here. So anyway, at this junction right here where these wires come together, going into that junction is the current I've called IB for current from the battery. Going out is the I1 plus I2. Now, plus because they are both going out. If I backtrack I2, that's leaving this junction, so is I1. So this is going to be 2.4 amps plus 6 amps. So we get 8.4 amps. Right? If I wanted to, I could calculate the power output at each of these. I'm going to go ahead and just and not do that. I'll talk a little bit about how I would, but I1 squared times R1 would give the power output here of bulb 1. That'd be 2.4 squared times 5. And that at bulb 2, we can get I2 squared times R2 would get the power output at bulb 2. By the way, power is also equal to current times voltage. So we should be able to take the current I1 and multiply the voltage across here, which is 12 volts. That should give you the same value as I1 squared R1. Down here we should be able to take, again, red to black, that's a 12 volt potential difference in this picture. We should be able to take I2 times 12 volts and get the same thing as I2 squared times R2. Anyway, purpose of this video is just to demonstrate, how to draw a simple circuit diagram and apply Ohm's law to find the currents. I hope that this successfully does that for you. Have a great day.